All right, welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Marilyn George, who is a PhD candidate at Brown University, where she is advised by Professor Cindy Kamara. Her primary interests are in applied cryptography with an emphasis on structured encryption. She's also interested in algorithmic game theory and privacy-conscious system design. Before starting her PhD, she obtained her master's from the Indian Institute of Science and was a research fellow at Microsoft Research India, working on analytics over encrypted data. And today, Marilyn will talk to us about structured encryption and dynamic leakage suppression. Thank you, Marilyn. The scene is yours.
Thank you so much for the introduction. I'm just going to share my screen. Is that visible to everyone?
Yep, all good.
Okay, all right. So hi everyone, thank you so much for coming to my talk. I'm here to talk about our work on structured encryption and dynamic leakage suppression. And this is joint work with Sunny Kamara at Brown University and Tariq Mohtaz at Aroki Systems. So why is data, before I start, I want to say, please feel free to jump in with any questions you have. I have material for about 40 to 45 minutes and I'm hoping to have a discussion. And if people are interested, I'm open to discussing open-ended questions as well. Okay, so why is data security and privacy important? On this slide, I'm going to show just 4 of the biggest data breaches of the last 2 years. And each of these data breaches cost millions of records, privacy cost, and billions of dollars in damages. And each of them was caused due to a different reason. So a vulnerability in the code, a bad configuration of a database, a cyber attack, like a mysterious cyber attack, an employee login was compromised. And there are many of these breaches happening all the time for a variety of different reasons from a variety of different attack surfaces. So what do we do about data security? So one solution is before uploading any client data to an untrusted server, let's encrypt it and let the client keep a secret key that only the client knows. And once this data is sent over to the server, now it's all right. Now, even if the server is compromised by an external adversary or an internal person, the server is malicious, it doesn't matter because only the client has the key that will decrypt their data. However, what if the client still wants to have some functionality? Specifically, what if the client wants to run queries like search queries over their data without having to download all of their data again? So the client wants to send a query to the server, receive the correct response to their query, and wants to do this efficiently without equivalently, like I said, downloading all of the data, decrypting it, and finding the response. So this is the question of encrypted search. And there are many different solutions that one could propose to this question. And each of these solutions has 3 different aspects. So functionality, which is how expressive are the queries that your solution can support. Security, which is how much information is revealed to this untrusted server while supporting these queries and responses. And efficiency, which is often measured in server storage, which is how much space does the server have to use, client state, which is how much space does the client have to have, and how much communication needs to happen between the client and the server in order to receive the correct response to the queries. And there are several cryptographic primitives that one can use to solve this problem, and each of them has different trade-offs on these 3 aspects. So for example, we could use fully homomorphic encryption, and that would give a high degree of functionality and good security, but not so much efficiency. And we could use property preserving encryption, which would give a reasonable amount of functionality and very high efficiency, but not so much security because it reveals a lot more information to the adversarial server. And then we have this primitive known as structured encryption, which offers a fair amount of functionality, reasonable security, as well as practical real-world efficiency. And this is the primitive that I'm going to talk about today. So I want to set up the definition of structured encryption. What is structured encryption? So say a client has some structured data, so a data structure, and this could be a graph, a matrix, an array, and the client wants to upload this data structure to an untrusted server. So it encrypts and uploads this data structure. And now the client wants to run queries over this structure and receive responses to their queries. So if the underlying scheme only supports queries, we call the scheme static. And if it supports operations other than queries, especially operations which change the underlying data structure. So if you can make edits to the underlying structure and your structured encryption scheme supports those operations as well, then the structured encryption scheme is referred to as a dynamic scheme. So there's a static scheme which only supports queries and a dynamic scheme which supports changes to the underlying data structure. So what is our model of mistrust? What do we mean when we say the server is untrusted? The adversary or the server is persistent. So the adversary observes all of the communication throughout the protocol or your scheme. So as the client uploads the structure and runs queries against it and receives responses, the server observes all of this execution and learns meaningful information about the data structure and the queries. And this meaningful information is referred to as leakage. And this leakage has been a topic of study, and people have been studying it from many different angles. So a few of the questions that people have asked about leakage in the past. So one line of work looks at quantifying leakage in terms of bits. So how much information is leaked by certain cryptographic primitives, and can we quantify it exactly in terms of the number of bits? Using the leaked information to attack structured encryption schemes. So leakage attacks were first introduced in 2012, and there's been a long line of work since using different aspects of leakage to attack structured encryption schemes. And crucially, there's a line of work in looking to eliminate leakage completely, or trying to study if we can hide leakage or different components of leakage from the adversarial server. And this line of work is referred to as leakage suppression. And that's the line of work that this talk also falls into. Okay, so before I get into leakage suppression, I'd like to set up some preliminaries, but I'll pause here if there are any questions so far about the setting, the structured encryption, the primitive. Okay, so I'm going to continue, but please feel free to stop me at any point. So I want to set up the data structures that we'll be talking about today. So one is an array data structure, which we can think of as just a set of values in memory, which can be read and written based on the indices. So just a simple array with a bunch of values in it. Another data structure is a dictionary data structure, and this is a set of labels where each label is associated with exactly one value. So you can retrieve or get the value corresponding to a label, and you can put label value pairs into this dictionary structure. And then finally, we have a multi-map data structure, which is a generalization of a dictionary, where now each label is associated to multiple values, and they need not be the same number. So a dictionary has exactly one value associated with every label, but a multi-map could have a variable number of values associated with every label. And it supports similarly get operations and put operations. Great. So now I want to talk about some common leakage patterns that I'll be mentioning today. So assume we have this multi-map with these 4 labels, and each of these labels associated with a variable number of values. And say this multi-map is encrypted using this structured encryption scheme for multi-maps. So how do we define different leakage patterns that this scheme could have? So the first one I want to talk about is known as query equality. So what does this capture? are two queries to the encrypted multimap on the same label. So say the client queries the server for label 1, and then queries the server for label 4, and then again queries the server for label 1. If the adversarial server can tell that the first and the third queries were for the same label, but the second one was not, then we say that this scheme leaks the query equality. So even if the server doesn't know what the queries are, if it just knows this information, which queries are the same and which queries are not, then we say that the scheme leaks query equality. And then we have the volume pattern, which is how many values correspond to a query. So if the client queries label 1 and sees 3 encrypted values coming back, and then the client queries label 4 and sees 1 encrypted value coming back, and the server can see the number of values that are being returned. So even if the server can't see the values or the queries themselves, just the number of values that are corresponding to the query, then we say that the volume of the query is being leaked. And so that's for queries. And if a structured encryption scheme also supports dynamic operations, and dynamic operations are ones which change the underlying structure, then we have some additional leakage patterns that are possible. So for instance, we have the operation identity leakage, or which operation is being run by the client. So like I said, there's a bunch of different operations that dynamic schemes can support. So say the client does a query, then adds a new label into the multimap, then edits an existing label in the multimap. And if the server can tell that the first operation was a query, the second one was an add, the third one was an edit, and so on, then we say that the operation identity is being leaked. So the server can tell which operation is running. And finally, we have this notion of operation equality, which is are two operations being performed on the same label in the multimap. And this is a generalization of the query equality for dynamic operations. So if we look at 3 dynamic operations being run by the client, so a query for label 1, a query for label 4, and then an edit, which is performed on label 1. If the adversary can tell that the first and the third operations were performed on the same label, and the second one was not, then we say that this dynamic scheme leaks the operation equality. And so that's it for the preliminaries. And so we return to our question of leakage suppression, or can leakage be eliminated completely? And this question has been explored for different aspects of leakage in structured encryption schemes. So in 2018, there was a static framework shown that could suppress the query equality pattern. And then in 2019, there was a line of work initiated on volume hiding, or hiding the volume pattern of structured encryption schemes. And since there have been many volume hiding schemes proposed. And so why are these two patterns interesting? So the first is that they come up in many places. So many structured encryption schemes leak the query equality and the volume. And further, it's not easy to suppress these patterns without introducing a lot of inefficiency into the scheme. So it has to be, you have to be a little bit clever about suppressing these patterns without introducing large inefficiencies. Okay. So I want to talk about query equality suppression and what are some approaches that one could use to suppress the query equality. So the first thing one can think of is something known as black box ORAM simulation. And what does this mean? We assume that the server has an oblivious RAM, and one can think of this as an array that the server cannot see into, and the server cannot see which locations of this array are being accessed. And the client has a data structure that they wish to simulate using this ORAM. So here's how that would go. The first step would be to flatten this data structure out into an array so that it can be stored in the ORAM. And then every query to this data structure would be converted into a series of ORAM reads and writes, and the final response would be returned to the client. So I'll just run through a few possible ways that one could simulate a multi-map using black box ORAM simulation. So say the client has this small toy example multi-map. So the first label has 3 values, the second label has 1 value. So here is one way that you could think of flattening out this multi-map, which is to decompose each of these labels and values and have one entry in the array for each label value pair. Right? So the label 1 becomes 3 label value pairs and label 2 becomes 1 label value pair. And now when the client queries for a label, we convert this into a series of reads and writes to this oblivious RAM. So say the client was asking for label 1. We convert it into 3 reads for label 1. So each of the values has to be read. And then we can return the result to the client. And if it was label 2, we have 1 read to the oblivious RAM to return the value that corresponds to label 2. Great, so that's one way to do it. But as we can see, there are communication overheads because there's like 3 ORAM reads involved for label 1. And there is some information that is leaking to the server. And this is like volume information being leaked by the amount of communication somehow. So that is one possible way to do a multi-map. Another way to flatten out this multi-map is to add padding into the second label. So we're going to have 1 entry per label in the ORAM. So the first label just is as is. We concatenate all of the values and put it into the ORAM. And for the second label, it has only 1 value. And so we concatenate it with dummies, and I'm using bot to represent dummies. So we add 2 dummy values into this and add it to the ORAM. And now when a query is executed, we convert that to 1 ORAM read. So we reduce the number of round trips required, and the response can be sent back to the client. However, this is a small toy example, and we have to add like 2 dummies already. So this solution is going to cost us in terms of storage. So there's going to be storage overheads to flattening a multi-map in this way. Okay, so we've seen that black box ORAM simulation has efficiency costs associated with it, and also has some leakage depending on what data structure is being simulated and how you've chosen to flatten it out. And we have to be careful about what is being leaked to the server, even if we use ORAM. Okay, so that's one set of solutions, which is the sort of general purpose way of simulating a data structure and suppressing query equality. So flatten it out, store it in an ORAM, translate all the queries into ORAM queries. And the other way we can deal with this is to design custom-made oblivious data structures. And this is a way of tailoring the obliviousness to the particular data structure. So say we have a multi-map and we have a custom-made scheme that creates an oblivious multi-map. So I don't think there is one, but there has been work in having oblivious trees, for instance. So this means that it reduces the inefficiencies because you're now tailoring the ORAM in order to have the best possible efficiency for that data structure. So on one end, you have this general purpose solution that you can use for any data structure, but it could have efficiency costs and some leakage. And on the other end, we have this extremely tailored custom-made solution for a specific data structure. And so it's a natural question to ask, is there a more general way to suppress query equality without being as inefficient as black box ORAM? So can we do something in between? Can we do something that is still general, but not as inefficient as black box ORAM? So it turns out that this is possible. and there was a query equality suppression framework introduced in 2018. And here's how that worked. The ideas in the paper were based off of the seminal square root ORAM construction in 96 by Goldreich and Ostrovsky. And the main observation was that the execution of the square root ORAM with a cache and a main memory could be viewed as a leakage suppression framework where a zero leakage dictionary was being used to suppress the query equality of an array. Right? So there's a query equality leaking array and a zero leakage dictionary, and somehow this dictionary was being used to suppress the leakage of the array. So this whole execution of the square root ORAM could be viewed as an instance of leakage suppression. And in particular, it could be viewed as a framework that could generalize to more complex data structures. So not just arrays, you could suppress the query equality of more complex data structures, and therefore you could apply this framework to structured encryption schemes for more complex data structures. And it turned out that this framework produced schemes that were more efficient than black box ORAN simulation, and also comparable to custom-made oblivious data structures. However, this framework would only produce static schemes. So what does that mean? Schemes that only support queries on the underlying data structure. So if the framework took as input a dynamic structured encryption scheme, it would output a static structured encryption scheme with no query equality leakage. So it would suppress the query equality leakage, but also take away the dynamic functionality of the underlying scheme. And so once again, we come to a natural question: can the query equality leakage be suppressed in the dynamic setting? Or is it possible to create a similar dynamic query equality suppression framework? And this is what we do in our work, and we show that it is possible. However, we ran into a number of challenges while doing this, and these challenges are partially due to our techniques, because we used cache-based techniques to suppress dynamic query equality as well. So the first thing that happened was that we needed to suppress operation equality across all dynamic operations. So not just the equality across queries, but also the equality across all types of dynamic operations had to be suppressed. And additionally, we dealt with the challenge of correlated leakage once we allow for dynamic operations. So what does this mean? This means that, say we have a scheme that leaks the operation identity, which is which operation is happening right now, as well as the volume leakage, which is the number of responses to a query. Then somehow these two leakages together could interact in ways that reveal the query equality. So for example, we could have a distribution, a multimap, where you have one query which has 100 results being returned, and everything else is somewhat short. And then the server sees, okay, 100 results are being returned for this query. And then the server sees, oh, the client is performing an add operation. And then the server sees, oh, 101 results are being returned for some query. So the server can somewhat easily infer that the query where the 100 results were returned before the update and the query where 101 results were returned after the update were equal to each other. So it has some relation to the query equality. And so we wanted to suppress this as well. And our approach to this was to start with a volume hiding scheme as input. So the volume leakage would already be suppressed. And then our framework suppresses the operation identity leakage as well. However, at the time, volume hiding schemes had limited dynamicity, which means they didn't support all types of dynamic operations. And therefore, our framework had to upgrade the dynamicity of the base schemes by supporting more dynamic operations. So we wanted to have a fully dynamic query equality suppressing scheme after applying our framework. Okay, so before I go into explaining how the framework works, I'm just going to pause here for any questions or any clarifications in anything I've said so far. Okay, so I'm going to go on with explaining how the framework works. So we have a client with a key and a multi-map data structure. So throughout, I'm going to be using the example of a multi-map and structured encryption for multi-maps, but our framework can use another data structure with its corresponding structured encryption scheme. Okay, so given this base data structure, we use two building blocks. So we use a volume hiding construction for a multi-map structure and a zero leakage construction for a dictionary structure. And these are our two building blocks for our framework. And our framework is parameterized by lambda, which we call the epoch length. And say for our example that lambda is set to 3. So what does that mean? It means that during setup, the client converts this multi-map by adding in 3 dummy labels. Now, what are dummy labels? They're just garbage labels that map to garbage values. So I'm using bot once again to represent that these labels are dummies. And these 3 dummies are introduced where the number of dummies is equal to our epoch length. And the client encrypts this using a volume hiding multi-map scheme. And the client also sets up a zero leakage dictionary of size lambda. So for us, lambda is set to 3. So the client initializes a zero leakage dictionary of size 3. And these two encrypted structures together are then sent over to the server. And setup is complete, and the client can now start running dynamic operations. So here's how that goes. Say the first operation is the client wants to query label L1. So the first thing it does is it runs a get on the zero leakage dictionary. So it gets L1 on the zero leakage dictionary and receives nothing in return. And all of this entire operation happens in zero leakage, so the server doesn't see anything about the operation. The next thing the client will do is to get L1 on the main multimap, on the volume hiding multimap, and it receives back values, the 3 values corresponding to label 1. But once again, this is happening in a volume hiding fashion. And so the server doesn't see how many values are being returned for this particular query. And finally, the client does a put where it puts back label L1 and its corresponding values into the zero leakage dictionary. So at the end of the first operation, the zero leakage dictionary contains label 1 and its associated values. And the client has finished performing one operation. Now say the next operation the client wants to run is adding a new label to this multimap. So how would it go about doing that? Once again, it would first run a get on the zero leakage dictionary and receive nothing. And next, it would now get a dummy label from the volume hiding multimap and receive like maybe 1 dummy value in response. But once again, this is a volume hiding construction. So the server doesn't see how many values are being returned. And finally, the client would put this label 5 and its associated values into the zero leakage dictionary. So at the end of 2 operations, now the zero leakage dictionary contains label 1 as well as label 5 and the new values associated with it. Great. So now, once again, say the client wants to query label 1. And this is where we have to now suppress equality. So the server should not be able to tell that the first and the third queries were for the same label. So how does that happen? The client runs a get on the zero leakage dictionary, but this time the client receives back 3 the 3 values associated with label 1, but the dictionary is zero leakage. So the server does not know how many values have gone back or what has happened there. And now the client performs a dummy get on the volume hiding multimap because it already found the value in the cache and receives back this one value in a volume hiding fashion. And now the client puts back this dummy that it just read into the cache. Okay, so at the end of 3 operations, the cache or the zero leakage dictionary is full. And this epoch length lambda equals 3 also defines the number of operations that a client can perform before the cache or the dictionary is full. So now that this dictionary is full, we say that the epoch has concluded or it is over. And now the client can no longer run any more operations without resetting the whole structure or rebuilding. And for this, we have a rebuild procedure. And what does this rebuild procedure do? It essentially combines all of the updates, all of the dynamic operations into the main volume hiding multimap, and it clears out the zero leakage dictionary so that it can once again be used for the next set, for the next epoch of operations. And we have to be very careful while running this rebuild protocol because we don't want to leak any additional information during rebuild, because we've been hiding equality and which labels are operated on and all of that so far. So even while running rebuild, we have to be careful about what is being leaked to the server and what is visible to the server. Okay, so our rebuild protocol is now broken down into 3 stages, which is extract and tag, sort and shuffle, and update. And the first phase is extract and tag. So what do we do in this phase? We essentially have to decide which entries in the dictionary and which entries in the multimap we want to keep for the next new structure that we're going to rebuild. Right? So how does this proceed? First, the client initializes a RAM, and this is, you think of it as an array on the server, an encrypted RAM, so the server can't see into it. And the client proceeds by first extracting each label from the zero leakage dictionary, which is by querying each of those labels, and writing them back to the RAM with an additional tag that we call freshness. So what is freshness? Freshness, you can think of it as a value that denotes whether we want to carry forward this label to the next data structure. And this value is pseudo-random if we want to carry it forward, and it's 0 otherwise. So label 1 receives a freshness value, label 5 receives a freshness value because it's a new label, and the dummy receives 0 freshness because we don't want to carry it forward. And then the client extracts all of the labels from the main multimap, the main volume hiding multimap, and adds them to the RAM one by one, tagging each of them with freshness. So everything in the main multimap receives a freshness value except for label 1 because it was already found in the cache. And the encrypted RAM is filled out and complete. So this finishes the extract and tag step. And once this is done, the data structures are discarded, and for convenience, I'm showing the RAM as only having the labels, but we should think of it as also containing all the associated values. So essentially, everything that we need to build a new structure is in this RAM now. And how do we go about doing that? So the first thing we have to do is separate out the stale values or the 0 freshness values. And we do that by sorting this RAM on the basis of freshness. So an oblivious sort protocol is used between the client and the server that sorts this RAM on the basis of freshness. So what is happening here is actually two things. The first is that the stale values or the zero freshness values are being moved to one side, or they're like being pushed out of the array to one side. And every other entry, which was tagged with a pseudo random freshness, is being shuffled. So every valid entry is being shuffled. So this oblivious sort achieves both these purposes for us, is to remove the dummy values, remove the stale values, and shuffle the fresh values. And once this is done, the client can tell the server to truncate or remove the stale values. So the server removes two values of the end. And now this RAM contains only fresh, valid entries that we want to include in a new volume hiding multimap or the new structure. And so the client once again sets up a volume hiding multimap and a zero leakage dictionary. Again, this dictionary is of size lambda, so it has 3 empty slots. And it reads each entry of the RAM and uses the volume hiding schemes update in order to add each of these entries into the main multimap. So at the end of the update phase, all of the new fresh values are added back to the volume hiding multimap. The RAM is discarded. And once again, we're back in some sense where we started. So, but the volume hiding multimap contains all of the updated labels and values. Once again, the zero leakage dictionary is empty. And the client can now start the next epoch of operations. And that is sort of how the framework works. So once again, to summarize at a high level what happens, there is a volume hiding main structure and a zero leakage dictionary. The client runs lambda operations in one epoch, which is like one set of operations. And at the end of the epoch, the zero leakage dictionary is full, and therefore it must be rebuilt so that the client can continue to run operations. And during rebuild, a RAM is created which contains all of these updates. And then this RAM is used to initialize a new volume hiding structure and the zero leakage dictionary. And then the RAM is discarded and we continue. So that was the framework summary so far. If there are any questions, I can pause for a bit.
Yeah, actually I have several questions regarding this
Okay.
design. So the first is regarding the zero knowledge dictionary, right? So I'm just wondering, because why you consider to put it on the server side? Because at the client, you still need to track the states of the dummy labels, right? So that you can, make it within the limits of the epoch. So, if you just put it on the client, you can also save the communication cost, right? So, and right now, because you already need to track this state.
Right. So that's a great question. So it turns out that you can think of the zero leakage dictionary as a client. So you could think of a design in which the zero leakage dictionary is being stored at the client. And currently our hope is that the storage that you need to track the state is much smaller than the dictionary itself. Right. So if it turns out that your state is as big as the dictionary and your client has enough space to store the dictionary, then you could move it to the client and treat it as secure because it's on the client. And that would change our efficiency numbers. But so far in our design, we're trying to keep the state minimal, maybe like counters, keys to pseudo-random functions, like as minimal as possible. And even throughout the rebuild operation, we are sort of constraining ourselves by forcing ourselves to use very little client state. But that's just like the choice that we made, and you could choose to design it differently if you keep the cache at the client.
Okay, so another question is regarding the parameter of lambda, because this is somehow, I just want to understand how you select this parameter, because I can see that if you have a large lambda, right, so that you can have like more dummy operations so that you don't have to trigger this expensive rebuilding process, right? So does that mean that we can set a very large lambda? So will that related to, I don't know, performance overhead, or there any trade-off on security?
Right, that's a great question as well. So yes, the lambda controls the epoch size, which is the number of operations you can run, but it also crucially controls the size of the zero leakage dictionary. So each time we perform this get on the zero leakage dictionary, it ends up being that the cost of that get is related to how big that dictionary is. So you could think of several different ways of initializing this dictionary, right? So you could have a naive construction where you just read the entire dictionary every time, and that's a completely zero leakage solution. But that means that the bigger your lambda is, the bigger that dictionary part becomes, and zero leakage in itself is expensive, right? So you can choose to initialize the zero leakage dictionary using ORAM of some kind, but even that is expensive. So the bigger you make the zero leakage part, the more operations you can run, but then the more cost you're paying on the zero leakage side of things. So picking the optimal lambda is actually a very interesting question. And like it could be independently studied for like different settings. How would you pick the optimal lambda? And in our asymptotic results, we pick lambda to be bigger of the query space of the main structure. So in a multimap, that would be the number of labels that are in the multimap. So that's sort of how we use for the asymptotics, but it's definitely a very interesting question to explore concretely for different settings, how you would set lambda and deal with that trade-off.
Okay, so my last question is regarding to the rebuilding process, because I can see that you somehow leverage server to assist this kind of rebuilding process with the client, so that you can leverage oblivious sort, right? So and the shuffling to do this. So I'm just curious because at the very beginning, the client has the data, right? So they can just encrypt, to build this, data structures at the client side, right? So why you just, download the encrypted data structure from the server directly, and you can decrypt them and rebuild the data structure from scratch? Because right now, if you trigger this oblivious sorting and shuffling, so which means that you have to involve like multi rounds of communication, and which is actually very, very expensive, right? So
Yep. So the oblivious sort itself, the way that we're doing it, it is particularly expensive. You could parallelize it to some extent, but you need to have more client state for that. So if, like you said, we do have the space on the client that can hold the entire data structure, then it makes like perfect sense to download the whole data structure and do the rebuilding on the client. But our assumption is sort of that once the client has outsourced the data to the server, it never wants to download all of the data. So it wants to have like some sort of bounded client state, which I guess in the case where you're like outsourcing your data to Drive or Google or something like that, you could think of it that once you've uploaded the data, you never really want to download all of it. You only want to download what is relevant, or like at most some small amount, if that makes sense.
Right, but from the business model point of view, because if the client outsources the data to the cloud, actually, the communication to the cloud is very expensive, because the cloud will charge the communication. So that's my concern. So
yeah, definitely. So it's also like another, I guess, thing to think about is if the client even needs dynamic query equality suppression, right? So it's like a very high level of leakage suppression. So it's in some sense a high level of security. And so you're paying for that high level of security. And it's actually a good segue to my next slide, which is actually like an efficiency comparison. So this is sort of over a sequence of lambda equals 64 add operations to a multimap containing 256 labels and 2 to the 16 values. And I'm comparing between our framework applied to AVLH, which is a volume hiding multimap scheme, black box simulation using path ORAM, and a standard dynamic EMM. So what we end up seeing is that our framework is sort of better than path ORAM, which is what the only option if you wanted to suppress query equality previously in the dynamic setting. So we're better than them, but obviously our leakage is a little bit greater than ORAM. So in some sense, we're leaking the total size of the multimap before and after rebuild. So after rebuild, the server can see, okay, this is the change in the total size of the multimap. And before rebuild, this was the size of the multimap. But for ORAM, if we're using black box simulation, we're just going to only ever leak large upper bounds on the number of labels and the maximum tuple length. But as you said, if you compare us to standard dynamic multimaps, we see that our communication is like far worse. And so there is like work to be done in sort of making this solution better. But in leakage, we do like much better than a standard dynamic EMM because that would leak always the volume and the query equality. So it's sort of, we're like the first sort of solution to have something that is better than black box ORAM simulation, but there is like a long way to go in terms of getting to optimal or even close to optimal communication. Okay, so in summary, we have a dynamic query equality suppressing framework, and it turns out that our framework also suppresses operation equality, operation identity. And so when we apply our framework to AVLH and PBS, which were two existing volume hiding schemes, we produce fully dynamic, almost zero leakage structure encryption schemes, which is also like a completely new construction. And then we show that our schemes are asymptotically more efficient than black box ORAM simulation. So please see our paper for more details. Thank you all for your attention, and I can take any more questions that you have.
Thank you very much, Marilyn, for your very interesting talk. Yeah, I might start with a question actually. Xingliang asked one of the questions that I had in mind. This one, I was also wondering about that.
Right.
I had this other question about these dummy queries. I guess there is a reason to query different dummies, but I couldn't quite figure out what's the reason.
Right. I might have missed saying that. So essentially, the main structure only hides volumes, right? So each time we want to query a different query on the main structure so that we don't reveal to the server that we are querying dummies. So if we only had like one dummy and we were going to reuse it every time that we query a dummy, then we're revealing to the server that you're reusing this entry. So the server can't see the volume, but it can potentially see the query equality on the main structure, right? Because the underlying scheme that we're starting with, okay, maybe I was not super clear about that. The underlying scheme that we're starting with is volume hiding, but it leaks the query equality. And that's what we end up suppressing. And so we need to have these unique dummies. Each time you make a dummy query, it has to be a unique dummy.
Okay, yeah, that makes sense. Thanks for that. Any other questions from anyone? We have time for questions. You can also write it in the chat or Q&A if you want.
Yeah, maybe I can ask another question. Maybe it's not very closely related to this paper, but because this is also related to the volume hiding, constructions, right? So because for the volume hiding, if I remember correctly, because you mentioned the paper in CCS, right? So the KM19, right? So because even in the CCS paper, for the volume hiding, I think they have the multi-hash data structure, but they also apply padding to the data structure to fully protect the volume, right?
Right.
Yeah, so do you think that will become some like necessary, countermeasures when we apply structure encryption to practice? So
right. Do you mean like lower bounds type of results?
Yes, to hide all the, fully hiding the response volume and size. Yeah.
Right. Yeah, no, that's actually a very interesting question. It's something that I've been thinking about a little bit, not too much, but something I'm interested in exploring is sort of the lower bounds in terms of, are there impossibilities? Is there a certain amount of padding that we have to add in order to, or a certain amount of inefficiency that we have to have if we want to hide query equality and volume at the same time, right? And there are like some lower bounds in the ORAM literature on like oblivious RAMs. And what we're doing is slightly different because first off, oblivious RAMs are sort of the underlying data structure is always like an array. and we have this more generality. We have support multimaps and like other data structures as well. And then there's also the question of like ORAMs don't really have resizability. So like they can't grow as the data grows. So we're also doing something of a different nature where like our structure keeps growing. So I guess those lower bounds are not directly applicable to us, but it would be interesting to know sort of where are the bounds and what does it mean in our setting. So it's something that I'm interested in knowing, but yeah, I don't really have like a clean answer for that. But yeah,
thank you.
Yeah.
Any last questions from anyone?
Yeah, I have a question.
Yeah, go ahead.
Hi, Mary. I'm Shifeng. Thanks for a nice talk. I guess you mentioned actually you give the dynamic suppression framework, which is designed from limited dynamic volume harding STE, right? Yeah.
Right.
Yeah, what does the limited mean? Does it mean it only needs to support addition?
Right. So the two base schemes that we used, so AVLH supports only addition, and the other way. PBS supports only addition, I think, and AVLH supports edits. So you have to have existing labels and you can edit them, but adding new labels is not so easy. So it's like some form of limitedness in how the underlying scheme supports dynamicity. And this sort of ends up like, so in our rebuild protocol is slightly different depending on the underlying dynamicity of the volume hiding scheme.
Okay, thank you.
So
I suppose that suppose that we have a fully dynamic volume hiding encryption. So in this case, can we simplify the dynamic suppression framework?
So that's a good question. We haven't thought about it too much because at the time there weren't any fully dynamic constructions available to us. But I would imagine you could try to simplify it, but at the same time, you still have to suppress like query equality, potentially operation equality as well. So I think you might still need some of the inefficiency, but maybe not all of it. But yeah, it's not something I've thought about a lot. So yeah.
Okay.
But there could be like a completely different way of doing it. Like if you do it in the cache-based, if you do it in the sort of cache-based framework, then I think there will be some inefficiencies. But if there could be like a very different way of suppressing query equality that I haven't thought of. Yeah.
Okay. Thank you.
Xingliang, did you have another question?
No, all good from my side. Yeah.
Okay. If there are no further questions, right. So thank you everyone for tuning in, and thank you very much, Marilyn, for your very interesting talk.
Thank you so much, and thank you for coming to the talk, and thank you for all your questions. It was great. All right.
Thank you, and hope to see
right,
everyone
thank you.
next time. Bye, everyone.
All right. Yeah. Bye-bye. Bye.
Bye.